I'm from Oracle Labs, and we've got a few hundred people scattered around the world working on kind of higher risk, longer term projects. And I think the most exciting one we have, although we have a lot of good stuff going on, is GraalVM. And as soon as Bob gets us going here, I'll talk a bit about that. All right. So, so GraalVM, and this talk is mostly about performance with GraalVM. So I gave most of this talk at the Silicon Valley Java users group last month, and I ended up getting a lot of questions about multilingualism and Polyglot, which I wasn't expecting. So I don't have as many slides on that prepared, but feel free to interrupt me at any time, and I can riff on pretty much anything. Yeah, okay, let's get going. So what is Graal? We have kind of 4 words I like to use to describe it. It's multilingual, it's efficient, it's secure, and it's embeddable. And so the vision is to extend the ideas that Java had back in the 90s of write once, run anywhere. Anywhere is kind of an ill-defined term. We want to write it once in whatever language you want, and run it in any application you want, which may be in another language, and run it in any engine you want, which could be like a node, it could be in a database, or standalone. And it's a very long-term research project. We started the project actually in 2011, but it's also the intellectual heir to a project that earlier started in Sun Labs called Maxine. It started maybe 6 years earlier. We launched this as an open source initiative last year, and this year we have a commercial version as well. It's an open course kind of thing. So we've always believed at Oracle in multilingualism. There always seem to be people that care passionately about various languages in various ways to define what is developer productivity, what makes programming intuitive. And so we wanted to allow that kind of discussion to happen independently of how to make the application run fast. So I'll talk a bit about all that. So GraalVM, one of the issues we sometimes run into it's kind of like a Swiss Army knife of VM technology. And the introduction that we do, well, we have a hackathon we do. We're going to do one next month at Oracle Code 1. And the hackathon is a top 10 list. Top 10 things you can do with Graal. And some of them are about multilingualism. Some of them are about ahead-of-time compilation. But one of the original research goals was to make it really easy to add your own language. We directly support a bunch of them, Java, JavaScript, Ruby, Python, and R. We also have an LLVM interpreter that we support, which can run any LLVM language by interpreting the bitcode that comes out of the LLVM front end. And so we support C, C++, Fortran, Rust, and so forth. So the static languages that like to ahead-of-time compile often have an LLVM front end. It was really designed to be embeddable. So 2 of the places we're embedding it now are NetSuite and the Oracle database. We also just had a goal to make a faster, more maintainable compiler for JVM languages that's flexible enough to work either ahead of time or at runtime. And the whole infrastructure is written in Java. The core is all open source, and the thing about it I think that's really differentiating that we've noticed is that it's very easy to extend. We can bring in a grad student who's maybe just starting their master's program, and they're productive on adding things to the engine in just a few weeks or a month at worst. Something that we didn't expect is actually quite as much commercial interest in running your own language. A lot of people have some sort of custom language or domain-specific language. For example, Goldman Sachs gave a talk last year at Code 1 and doing one again this year on their proprietary language called Slang, or for security language. And they've been able to port this. They got it running in like 6 weeks on GraalVM. Of course, tuning it is still an ongoing project. We also have an embedding API to integrate Graal with other engines, and a plugin layer to kind of plug in your own operating system if you want. That's what we use when we run in the database, which likes to not do things the POSIX way. It's also useful for embedded platforms. This technology has been in production for a while now. I mentioned NetSuite. Twitter has been using it probably in production at the largest scale for the longest. And they say they're saving millions on it, which is awesome. All right, so let's talk a little bit about it. Yeah, so as I mentioned, there's two versions, a community edition and enterprise edition. Enterprise edition is mostly about performance, security, and scalability. The goal that we have is to make sure that anybody running on enterprise edition can always downgrade. So if you want to, not pay Oracle, you can always pay more to Intel and PG&E. So as I said, it was a research project. We were very modest in our ambition. One VM to rule them all. We don't talk about that much anymore, but that was really kind of the idea. You kind of get more cheeky when you're just a bunch of grad students. So as I said, Graal is targeting OpenJDK. It also runs dynamic languages and native languages embeddable in these different platforms. And one of the things I think is really exciting is that there are a lot of cloud native frameworks that have been springing up literally in the last year that are really focusing on making sure they can certify to run on GraalVM because of ahead of time compilation, giving them fast startup and low footprint. So some people do feel like, okay, well, because Oracle does Java and we do Graal, that they somehow, Graal is therefore just favoring Java. No, we want to make sure that we love all the languages and not just focus just on Java. But obviously Java is the biggest slice of the pie here. But our goal is to go through a bunch of these slices of pie. Sometimes I get asked, well, why did you choose the language we chose and not other languages? Why aren't you supporting Visual Basic or PHP? And the reason is we basically looked for the languages that had the largest open source ecosystem. And so that's where I thought there'd be the most value in having, the mix and match. So when you pick a new library, it might be in a different language. I want a Python machine learning library. I want to integrate it into my Java program that's doing some data management. There's zero overhead to integrate and no cost to pass objects back and forth or to cross that function call boundary. So as I mentioned, there's two major ways that you can run Java programs in Graal. There's the standard way we're used to it. You just type Java, run the class. It runs with OpenJDK. And then there's a ahead of time compiled mode where you first build a binary and out of the class file, and then you can just execute that like any natively compiled program. So, of course, these two different kinds of compilation have trade-offs on a number of metrics. So I'll talk about those. So just JIT versus AOT, you can see that JIT compilation, at least today, gives you higher peak throughput, and the garbage collection quality is better on a JIT. And so the maximum latency that you have for a GC pause is better. Ahead of time compilation gives you faster startup speed, much lower memory footprint, and smaller packaging when you want to deploy in devices. So now, one of the things I want to do is explain more about native image because that's one of the major new things that we have. And the way this works is that we actually run your program. The native image build tool runs your program in Hotspot, and we iterate where we analyze all the classes we can find. We run their static initializers. We snapshot the heap, and then we find if there's any unresolved references, and we kind of iterate until we get to a fixed point. And then when we do that, then we ask the JVM, hey, please generate machine code for all the classes that you found. We also then write that out in a traditional executable format, like an ELF binary on Linux, to a native executable. And so the interesting thing here is that normally in a JVM, the code you're running, because it was JIT-compiled, is running in the heap. That's where it lives. AOT compilation is running in the text segment, and that means it's shared across processes, and the OS can do more tricks with stuff in the text segment. And that's interesting for a lot of cloud deployment scenarios. So when you do a JIT compilation, here's what happens when you start up all those different things. Let's see if this will work. I got this pointer, I think it's so cool. So you load the executable, you load classes, you verify bytecode, you start interpreting, et cetera, et cetera. You go through all these different things. And then of course, there's actually multiple levels of execution in the JVM. So the first one is you run in the interpreter, and the interpreter is gathering a profile on what the program does. And then there's a simple compiler called C1 that does a quick and dirty compilation. And then we get some more feedback, and then we run the C2, which is the server compiler that's going to get a second more aggressive compilation tier that's going to spend more time compiling and generate better machine code. And that's what happens for the hottest functions. Your function, if it's not very hot, may never get past the interpreter, it may never get past C1. With AOT, when you start up, the executable is already loaded, the heap's already prepared, and you already start with the best machine code. And so instant startup and low footprint, improve a lot of different things. And so the most important thing I think that they improve is robustness of your program. Any program that's ever been written by humans has some way of getting hung or having leaks of some sort. And the best way to date that we know how to make sure that programs are correct is to turn the program off and on again. So if you can do that really fast without any penalty, just keep doing that. To the extreme where we believe that in the future we'll be able to basically boot from a hypervisor every time you get a request from HTTP, get that done in a few milliseconds, and at least get into a Java stack, do some nutty stuff, and get out. And that's all very possible. Cost, one of the things that you typically do in a cloud today is you keep a container up and running just in case some work shows up. You don't want to have cold starts if you're running in something like Lambda. And that means you have, at some point, lots of CPU threads and lots of DRAM that's committed to your application not doing work. So the faster you start up, the less of that you have to deal with. And then the other major thing that I think is pushing people toward this model is security. So in the past, we had some big monolithic application with some big cache of data, multi-gigabyte heaps getting toward terabyte heaps. Then you end up having more security problems because there are side channel attacks like Spectre and Meltdown, and you can't really rely on any in-process isolation to do a job that's going to mitigate all the known vulnerabilities that we're finding because of micro-architectural side channels based on timing. So I think that the minimum you need now is process isolation, and so that's one of the things you get as well. It makes it a lot easier if you have a fast startup and low footprint. And then, people are kind of, whenever people talk about serverless and you say, oh, you have to get rid of state, it's always so bad. But, if the state is something that you can put in your static initializer, rebuild every time, then you can do more work without, you can serve more stuff from cache without having to necessarily pay that overhead if it's in the text segment. So any data that you have in a cache that you pretty much need all the time, you can pretty much put metadata and just go put it in your static initializers, set it all up at build time, build any object graph you want, and serialize it into the text segment. So anytime your metadata changes, you add a column to a table. Anything else that you might have, some object relational mapper with some metadata for, just build all that introspection into the static initializers and make sure native image is generating it. And I see that actually the Micronaut folks have just announced that they have some pre-compiled data at runtime project that is doing that kind of thing. I think that's exciting to see that frameworks are starting to pick up on this from GraalVM. So in terms of startup time, AOT versus the just-in-time compilation for these frameworks that we looked at, which are Helidon from Red Hat, Micronaut, and Quarkus. Quarkus is from Red Hat. Micronaut is an independent open project. You can see they get orders of magnitude faster to start up with the time compilation versus JIT compilation. Memory footprint, maybe get 4x improvements, 3 or 4x depending on the platform and how well they've optimized it. So for memory footprint, well, what is it you get what is it you need to keep around with a JIT that you don't need with ahead of time compilation? Well, so I'll just skip here. You need an executable, obviously in both cases, but you have to have the byte codes that are going to execute the program in addition to the machine code, so that's kind of double. Then you have to have all the metadata needed to do reflection. You have to have a code cache. You have to have profiling data. And of course, the compiler itself has space and it has its own metadata and its own data structures that it uses to compile methods. And so that's a lot of overhead that you get to avoid with ahead of time compilation of Java. Sorry, that slide is in there twice. here's another benchmark we did. This is Quarkus starting up and serving a couple requests in the first 10 seconds. And so the other thing that I think bears mentioning here, and you can see in these two graphs, is that here when you're starting up in a JIT compiler, all this, this noise here is the compiler waking up and starting to compile methods that it sees are hot. And then when you're serving requests, here you can see there's a little bit more width to these requests going on because they also may trigger some methods becoming hot that require a few more methods to be compiled. Whereas in the ahead of time compiled mode, these lines are just straight up and down, so there's no extra work going on there. And the number of cores needed to just start initializing things, you can see here, Quarkus is using like 5 CPU cores to wake up and start initializing the application, and we're using less than a core with the ahead of time compiled version as well. So, you know, there's a trade-off, right? That the peak performance is not as good once you start getting millions of requests. Ahead of time compilation is going to see a little throughput loss. But there's a step we can use to deal with that, and that's profile-guided optimizations. So in the normal JIT mode, when the system wakes up, we profile and we compile code around just what your program did at runtime, and that might be sensitive to the data you're actually using in this particular instance. Profile-guided optimizations, you know, you have to kind of, at development time, run tests that are relevant, and get workloads from those tests, generate profiles, and then build again a second time to get a better performance. This is a little bit old data. We've actually fixed that little dip there at the right. That was actually a bug. But you basically get comparable performance with ahead of time compilation to at least the stock JDK compiler. The Graal Enterprise compiler is above the red line there, another 20%, not shown on this graph. But we think there's a lot more that we can do in profile-guided optimization to make sure that in the future we'll get it better. So peak performance, as I said, startup profiling at startup gives you some better optimizations, and you can make optimizations about profile and de-optimize. So one of the things that differentiates the way, like let's say the compiler in Hotspot works from say something like LLVM, is it doesn't just optimize, it de-optimizes. We make aggressive assumptions. Hey, I see this thing always seems to be short and fit in a couple bytes. We'll optimize and generate code for that. We put in a little guard. If we see something that violates the assumption, we actually de-optimize the code, throw it away, go back to the interpreter, reprofile, and then generate something more general. So the ability to de-optimize does give us an advantage in that we can make more aggressive optimizing choices. Of course, in ahead of time compiled mode, we have to handle all the cases in machine code. So we can't just hang around hoping that some code paths are never going to get hot. But you know, PGO helps. And the nice thing about AOT is you get more predictable performance. I'm sure anyone who's worked with Java and performance for a while has often find actually get a lot of noise, you know, in terms of what you see in different runs, because it chooses to compile methods in a slightly different way. The warm-up happened, you know, there's a lot of kind of, what's the word for it? Non-deterministic kinds of conditions that can affect the way a JVM will perform. And so that's something that you see more stable with AOT, and that can be helpful for people. So optimizing a compiler for too few benchmarks results in a lot of overfitting. So we started a new benchmark project that we thought captured more modern Java workloads. So you'll see, for example, a lot of Spark benchmarks in here. You know, your mileage will vary from benchmarks. What we wanted to do with this benchmark that we did, and you can see more about it at renaissance.dev. This is actually a paper that published at PLDI this year in cooperation with 4 universities around the world. And really just to show that the Graal is competitive, Graal Enterprise gives a lot of performance improvements, and it's worth it enough that you should check it out on your own application, because of course, benchmark numbers don't matter. What matters is performance on your app. So hopefully this will just be enough of an incitement for you to check it out yourself and try it and see what you get. And these are all numbers done with the dynamic JIT compiler. As I mentioned, you know, performance. You know, you see a lot of noise. This is actually our internal benchmark server. So you can see over the this is a I think the first graph here is 2 months, the bottom one is 2 years. You can see a broader trend over 2 years, but on each individual commit, it's sometimes hard to figure out what the impact is. And so this is one of the things that in general, of course, makes performance hard to test. So what I wanted to do is go into a little bit of what we do when we're tuning performance with Graal, and show you a bunch of different use cases that are doing the same thing. So if you look at these use cases here, you might have an opinion on which one is faster. But of course, if you start putting in optimizations, you get different things are happening here. So in example 3, we're creating an object, and because this is basically boxing the value of the integer. Graal actually makes this third example the same performance as examples 1 and 2, which you kind of expect to be the same. So Graal is very, very good at unboxing primitives. It basically always does it. The compiler C2 that's in hotspot sometimes does it. So sometimes people will try to help C2 out by unboxing things for it. So here's an example of where someone has tried to cache like the unboxed value or cache the array lookup. But the thing that's interesting here is the C1 compiler is actually faster on example 4 than example 3 because you don't have to create a box on each iteration in example 4, but because C2 and Graal both can eliminate the boxing, they're actually slower on this 4th one than on the 3rd one. So I guess the moral of the story here is don't over-optimize at this kind of micro level. Spending too much time on these micro benchmarks can be fruitless and damaging to your psyche, so I don't recommend it. But we do that for you, so you don't have to. This is a JFR log. People don't often realize that when you get a Java flight recorder, it's not just recording what the application is doing, it's recording what the compiler is doing. So this is what we use to see when the compiler is doing work. This is typically, if you call us up and you have some sort of bug, or if you post an issue up on GitHub, then we'll often ask for the JFR graph so we can debug what's going on. I mentioned a couple other dimensions that I didn't talk about, max latency. So in the case of JIT compilation today, you've got a lot of low latency garbage collectors available. There's G1, there is concurrent mark and sweep, there's ZGC, there's Shenandoah. In AOT today, we only put in a simple stop and copy collector. It's basically designed for small heaps. And it's really designed for that case where you're turning off and on your program a lot of times. So you don't really expect a lot of GC load. And so the load balancer effectively is kind of like your GC. And all GCs, of course, have a throughput versus latency trade-off in that the more parallel they are, the more work they have to do that slows down all the throughput. So if you reduce the maximum pause time, that means all of your applications get a little slower by putting in more instructions to do save points. And whereas stop the world GC has the most throughput, but that means you have the highest pause time. Packaging, I mentioned that. So in Java world today, we have JLink to get a smaller package. You can make a lightweight Docker image. With AOT compilation, everything's in a single binary. It can run on a bare metal Docker without an OS in it. So you typically see a lot smaller constant overhead. All right. So, and then of course, there's trade-offs that we're making here. Peak performance versus packaging trade-offs. If we inline more, we get better peak performance, but the package gets bigger because we're duplicating more code. Now, so I said, so far that today we have a lot of downsides to AOT. And so the question is, can you really have your cake and eat it too, as others believe? So the first thing we think is we can do a lot better job with profile-guided optimizations. We're going to have a new garbage collector to go into native image as well. And we have a new way to generate the deployment parts of native image, which requires that you trace, you use an agent to find all the reflection usage, and we can use that at build time. So we're hoping that we can actually get improved comparable performance, at least, or peak performance and max latency characteristics with AOT compilation as with with JIT compilation. One of the problems with doing a profile when you warm up a JIT program is that the profile during warm-up may actually be polluted with initialization work that can be not indicative of what happens over the long term of your application. So if you're doing a profile-guided optimization, you get a lot longer profile, and that can sometimes give you better data. So we think that can help us. We've already done the work to make the compiler work with other GCs in JIT mode. So we feel like it should be fairly straightforward to give you a few more GC options in ahead of time compiled mode as well. All right. But beyond just running Java, we can do a lot more. So here I have a little Node.js program, and it's requiring a little JavaScript module here. We're just a little listener, but because JavaScript doesn't have a big integer class, we're going to go grab it from Java. And I can just use that object in JavaScript like it was a JavaScript object. And then what I'm going to do is just call, this is the one API we've added to all our languages, polyglot.eval. You just give it the name of the language and the string to run, and we'll just compile it and run it. And because we inline it all, there's actually no overhead versus calling the same functionality in the same language. And that's really useful because, hey, my JavaScript program can really deal with very big numbers. And I can use R's plotting facilities, and R has really, really good plotting for a lot of different use cases. Okay, so the way the infrastructure for Graal works is that, let me maybe switch to another deck. And I can. So the question is, can I explain a little bit more about how the multilingual support in Graal works? So I will go to another deck I have to talk about this. And you can make me go off script, that's okay. Do this all the time. Let's see what I want here. Okay. All right, so basically what happens is we have this API, it's called Truffle. And Truffle is an API to write an interpreter with. And so every time you add a new expression or a new statement in your language, you write that by inheriting from the Truffle interfaces. And then when you're running your interpreter, and everyone's probably taking an introductory compiler course, hopefully as an undergraduate, has done one of these interpreter things, knows it's simple, but they end up being very slow. The thing about Graal is it uses a technique called the Fujimura projection, which has been taught since the 70s. It just hasn't been executed in a way that's provided comparable performance to a handwritten compiler. The compiler watches what the interpreter does, and it generates machine code snippets for you. And what this means is that each of these languages, these are just Java programs that are interpreting the source code of that language. So when you put them all together, it just look like one big union language of all the different sub-languages, right? And so that's what allows you to add a new language quickly. So we have a little example program, if you go to graalvm.org, called Simple Language, and people have used that to implement SmallTalk. The slang guys at Goldman used that as well. A lot of academic projects have done it. We did an binary assembly interpreter and JIT-compiled that. So it's really take in anything and compile it to anything else toolkit. We wanted to demonstrate that from kind of the research point of view to show that we were complete enough to implement the weirdest languages across a wide variety of things. And one of the reasons we spent a lot of time on Ruby and R is that they have a lot of weird features in them that have been traditionally not possible to implement on top of Java bytecode as the execution infrastructure. So when people ask, how does this relate to OpenJDK and what do we see as the future of this? One of the things we have, versus OpenJDK, the thing to recognize is that the fundamental design choice of OpenJDK is that all programs that are being executed have a Java runtime defined by the Java spec, and what that Java runtime is, it takes bytecodes and executes them. So for Graal, Java bytecodes are source code for us, and it's not something that we require to execute programs. So what you're executing is really the AST, or the abstract syntax tree, of the programs after they've been parsed and run through the interpreter with a profile. The other thing that's cool about Graal is it's written in Java and it compiles itself. And so we've been able to write it in a much higher level way than the way existing compilers are typically written in C++ or something like that. And it's easier to extend. So you aren't writing compiler optimizations at the level that realizes it's a compiler. It says, oh, I have an expression node and a left operand and a right operand. That's not the way you write code. You write it kind of a higher level, like a Java application, and that makes it much more productive. So as I said, it's not really a runtime, it's a meta-runtime, so it runs things that run languages. One of the things that we've done is, of course, we extended Java a little bit for the infrastructure here so that we can support all the things that native code does. We call that system Java. That's kind of an internal implementation detail. And we do have two ways to run Java. So today, in production, you still are running Java on bytecode or you're ahead of time compiling it. We don't support Truffle API for Java, but that's actually a research project that we'll talk about probably in a few months. We'll have some results on that to talk about. But the other issue that we have when you're supporting multiple languages is that a lot of languages are really just glue code for native libraries. So if you look at Python, if you look at Ruby, you look at R, JavaScript has Node. A lot of the things you want to do to write a real application are really done in practice by native code, and Python, for example, is just gluing together ML libraries that are typically written in native code. That's a problem for us because then you have JNI, and if you've ever dealt with JNI, there's a lot of hassles with that, and there's performance overhead for that. It also means you lose safety properties. So what we did is we wrote another interpreter for LLVM bitcode, and so all the libraries that are written in C or C++ or Fortran or whatever, we can JIT compile them all together as another truffle language, just like the native code version. And the performance of it's pretty good. You pay a little bit of a price because the compilation isn't as tuned. We're not a super mature C compiler yet. But you make it up often in the case where you're going back and forth between the native code and the dynamic code, where that's typically pretty expensive. And so what we actually see is for, let's say, large Ruby workloads or large Python workloads, if they're going back and forth a lot, you see a win. Yeah, so that's mostly what I wanted to talk about there. Oh, this one other thing I guess I mentioned I could have, I showed you that slide before. So native image can pre-compute data node at build time. I kind of waved my hands a little bit at this. But with a regular JVM, you're first compiling the source at build time, and then at runtime you're loading a configuration file and you're running the workload. One of the things that you see the biggest benefits are on is not just the code that you're doing at build time, but any kind of configuration, like loading a configuration file and using Jackson or something like that to parse it, and then building up objects and data structures around that. You have now the choice of doing that at build time, and I think that's a really huge dimension of flexibility. So back to my originally. Did I answer your question? Yeah. Okay. That was a long answer. Let me get my mouse back here somewhere. Close this. Back here. All right. Great. So people sometimes wonder, like, yeah, is this multilingual thing, really valuable? Is it really useful? One of the most interesting use cases we see a lot is where you have a basic application, maybe very large, like NetSuite or some large application suite. But then you want to customize it and allow users to upload code at runtime to customize it. And so people want to do that with a load balancer. They want to customize that with JavaScript. So there's a lot of sandboxing features that we give you to allow you to run that dynamic language as a configuration on top of something like Java. I mentioned domain-specific language as a use case. Obviously, anyone who's been using Nashorn and Rhino should use Graal instead. It's way better, and it's also being actively maintained, and it's up to date with the latest specs. And you can see that there's a lot of places where you can actually start seeing performance benefits for Node, and of course your mileage will vary. but we're starting to see places where we actually get ahead and not of a custom designed compiler that was done for JavaScript, like the one that's in GraalVM JIT. I mentioned sandboxing. So we have a lot of features to help you embed Graal in your runtime. So the JVM, you're only allowed to have one VM per process. With Graal, you can have as many VMs as you want. We have this feature called isolates that allows you to create separate Java heaps that are isolated, as it sounds like, with no way to reference objects outside that heap, and you can throw it away separately. And you can configure the access control of the host program. Say, all right, well, I don't want in this host program, like that JavaScript customization framework, I don't want it to be able to like load more classes. I don't want it to be able to directly call native interfaces. I don't want it to do I/O. So we have a lot of things that we did to help restrict access, constrain resource usage. When you have these kind of embedded environments where you want one language embedded in another language that may be for a different purpose with different trust levels. Yeah, so that's the story there. You have this context API that's there in both Java and C. Oh, question, yeah. Yeah, everything functionally, the question was, are all these things in the community edition? Anything functionally that works is in the community edition. So we want to make sure that any application that works on enterprise also works on communities. You can always downgrade. I have it. I don't know if I have it in this slide deck. I have this little marketing slide called smooth downgrade. You know, and we want to make sure that if you ever get sick of working with Oracle Labs on this, you can always just downgrade to community and pay more to Intel, and fix your own bugs. Okay. So another thing that we did, because Graal is interpreting native code, is we can actually run native code on the VM infrastructure. So every time you ask for malloking a byte, set of bytes, we can make it a Java byte array. And so if you have like an off by one error where you're overwriting memory here, it's a pretty common case if you've ever written scanf code in C. I have an 8-byte object and I'm actually asking for index 8 and count from 0, not from 1. So that would be a bug. It would start overflowing and scribbling on your memory state. In a C program, that's going to start overriding random memory. This is a Graal Enterprise feature, so that you get this bounce checking protection in Graal Enterprise. And the API, the virtualization control is enabled in Enterprise. It just lets you do anything you want in community. So always make sure that you can downgrade. Then we also have some tools. So Visual VM we inherited, and we've been investing into. Be Graal aware. So here you can see this is a heap histogram, and you see there's R objects, there's JavaScript objects, there's Ruby objects all here on the heap, and you can see how much they're all taking up in terms of space. We actually we're going to invest more tools in this, and we'll announce some of that stuff next month. And what that really gives you is we also have a way to support the Chrome debugger, so you can debug any GraalVM language program with the Chrome debugger protocol, and you can walk through the stack and you can see all those different language objects there as well. So when you add your own language, you can reuse all these different optimizations, the same tooling, the same interop story. You can use the interop story to get back objects from other runtimes and all the security features. And then you can embed it and run it in any other engine you want. So hey, if you have your program, it works outside a database, it could work inside the database. If you write a program that runs in Node, you can run it outside of Node. It gives you a lot of flexibility to do those kind of things. And so when you add your own language or little languages, you get your own tools, and you basically don't have to reinvent the wheel to make a new language. And we're starting to see little things that are not much more than a library kind of use the language interop. The GraalVM community is pretty active. This is actually a pretty old snapshot at this point. But if you go there, you'll see we actually have we just hit 10,000 stars actually this in the last week, which is pretty cool. And we've had over 100 committers, and we've had important commits from Intel, Red Hat, ARM, AMD. So that's been great. And of course, over 100 different university students have contributed over the last N years on the project. I think actually in the these numbers are a little old in terms of how many issues and fixed. I think we have like 300 some open issues, and we fixed like 600 of them so far. So we're pretty active on GitHub and responding to your issues. We've been moving fast since we launched the project last year in April. I think we've had like, this slide is actually from a few months ago. So this is 22 releases. We're on 19.2 now. 19.2 will actually drop tomorrow. So 22 releases in the last 17 months. Lots of GitHub issues closed. Different features we've added. You have a choice now on when you initialize classes to either do them at runtime or at build time. Before that wasn't an option. We did a lot of stuff to support migration from Nashorn. We demonstrated running Python on Graal in the database. I mentioned the managed mode for LLVM. Compressed pointers and isolates support came this January. libgraal is a neat thing, which is kind of talking about how meta Graal is. We use native image support to compile the Graal compiler so that, I mean, it used to be last year when you wanted to run a program in Graal, the first thing would happen is Hotspot would compile the Graal compiler, and that would start compiling your program. And so JIT compilation mode had slower warm-up than Hotspot. So now what we did is we AOT-compiled Graal, and we call that libgraal. And so we link it in natively into Hotspot just the same way that, the C2 compiler in Hotspot's linked in. And then the native image agent is something that traces your usage of reflection or other runtime features so that you can configure them at build time just by running, running through a profile on sample workloads. And of course, we're also active on Twitter. Please follow us on Twitter. And we have a number of very active Twitter users. So, and as they're down the street too, and big users of Graal. So we are pretty active there as a way to interact with us, as well as Gitter and GitHub issues. And I think that's all I have. Oh, question?
Another is in terms of features, if I get at least, let's say if I get a big existing Java app and I just swap basically hotspot VM to Graal, can I expect it to work right now, or?
I didn't quite get the question. Can you expect more what?
Can I expect it to work if I just basically swap?
Yeah, so if you just drop in Graal, you set Java, you basically download Graal, set Java home to point to Graal home, and it's just going to work. We've never had any sort of functional problems where there's some Java program that works in Hotspot that doesn't work in Graal in JIT-compiled mode. In native compiled mode, there's obviously a few things that you have to do to make sure that we can make the assumption that the program is all known at build time. But that's what the native image agent does, is it watches what your runtime does, it creates a profile out of that, puts that in the build time image so that at runtime, when it tries to do dynamic things, we know we have all the dynamic code available in the binary, so we don't have to actually go dynamically load more code. You can keep with the closed world assumption. Okay. Answer your question?
Yeah, and in terms of performance, how are they comparable, like Hotspot with Graal?
Our goal is that the average performance of Community Edition be equivalent to the average performance of Hotspot. Your mileage will vary, of course. For Enterprise Edition, any regression from Hotspot, for even weird cases, is a bug. And in practice, we see about a 20% performance improvement for Java. And for Scala or kind of the more complex and the more abstractions you see in the language, the more more goop there is to dig through and for the compiler to eliminate. That's why people that are using Java 8 streams or lambdas, or they're using Scala or frameworks that have lots of objects allocating and kind of temporarily for various purposes. Graal is super good at limiting those, and that's where you see the higher speed ups. But the point is, you just try it out. It's super easy to try out and see what happens. One more question.
Edition trial. Excuse me. How long is Enterprise Edition trial, and where can I get it?
Infinite. The trial version of GraalVM, you can just use as much as you want for evaluation and testing purposes, right? It's just at runtime, then we ask you to pay us.
All right.
Yeah, so.
My second question is for profile-based optimizations, right? That collection of profile is obviously taking some time from processing of regular requests. So what's the latency hit if I enable that flag and let's say, let my server app run, I don't know, for a month?
Yeah, so you're profiling, you're talking about doing the profiling for native compiling, you know, while you're running a production system?
Yeah.
Okay, so normally people do the profiling for native image, you know, on a development or test system rather than running it on a production system. There is overhead to it. I don't actually have a number I'm going to quote. It's pretty similar to what happens if you run profile-guided optimization in a C program.
Okay, thank you.
And you have to, because you have to generate a bunch of file I/O to keep track of what the compiler did. So I mean, if you find a use case, we actually are looking at ways to do that. Like if you're spinning up like 1,000 nodes, maybe what you want to do is take the 1,000th node and use it to conduct experiments where it won't have an appreciable effect across the cluster, and then you could do something more dynamic. But you know, if you're just running on a single laptop, you probably don't want to do that for sure. More question.
Okay. What happens to the JVM TI interface, API, and the Java agents?
The Java what?
What happens to JVM TI and Java agents under Graal?
Yes, JVM TI problem. Okay, very good question. So if you're in native image, JVM TI today doesn't work. And so you need to do your instrumentation. And what people typically do is you do your debugging and make sure everything works on hotspot, and then deploy, you know, n instances in the cloud where you don't want to connect an instrumentation agent to all of it. We are working on something to address that. The problem with the Java instrumentation agent is that it's based on Java bytecode, and it wants to be able to inject Java bytecode into your program, which we generally may not have for a lot in a lot of different usage models. But we want to be able to inject code into running programs, and so that is an interesting project. We're working on it. It's probably not going to be there in the next 12 months, but I think it may be, you know, maybe a little longer than that, but not that much longer than that. The other thing that we're working on also that you didn't ask me about, but I'll answer anyway, is Java Flight Recorder. We are going to support that in a shorter period of time in native image. But again, today, diagnostics, debugging, do it on hotspot. That's generally seems to work. Huh? APMs? Well, I mean, if APMs are, sometimes they're just code you link in your program, and that's fine because it's just a Java program. If the if the APM is dependent on the instrumentation agent, I mean, usually there's different ways APMs can monitor a system. You know, if they're monitoring a C program, then they obviously don't expect an instrumentation agent. If you're monitoring Redis, for example, you just watch the requests coming in HTTP or what have you, right? So you can always do that. You can always link in something, which is what people usually do with native code that they want to use APMs on. So native image compilation today, it works like you expect native code to run. And you can debug, by the way, in Graal Enterprise, you can debug with any of your native tools. You can use, that's what we do, we use vTune, we use GDB, all your favorite native debugging tools rather than Java debugging tools when you do ahead of time compilation. Because it looks like an ELF binary then. I had a question over here.
Thank you. Yeah.
I'm doing a clockwise thing.
What was that?
I'm sorry. I mean, I waited. You were waiting. Came around clockwise here.
No problem at all. I'd read about or seen a talk from Azul Systems. Some of the things they're doing with, I think they called it like Java on Crack or something, where they're trying to do a lot of that profiling using hotspot and then somehow checkpointing the state of the JIT. And it's kind of sounding like you might need to do some sort of similar activity, or maybe you skipped over it. I didn't see it in the talk, but you're talking about.
That's a good question. So the question is around checkpointing Java versus native image compilation. And so actually, not just Azul, I think there's someone from Red Hat that gave a talk a month or two ago on doing checkpointing for Java. And it's been something that's been looked at for a long time. It can be effective. The issues usually are around what happens with the native code, which can kind of be problems. But the big reason that we want to use checkpointing is it doesn't make your image smaller, right? So you still need all that JavaVM runtime stuff. So if you actually look at the benefits that you get when you're deploying Graal in a cloud, What's much more important is reducing the memory footprint. Like if you look at Lambda, you pay by the gigabyte second. So it's just as good to reduce the memory usage by 20% as reducing the code execution time by 20%. It's actually much easier to reduce the memory space by 20% than make the code 20% faster.
Yeah. But if you reduce your memory, don't you also get less CPU in platforms like Lambda?
If you reduce the memory, lots of things happen. So, and actually, if you build a system today, and on typical deployments, you spend more money on DRAM than you spend on processors. DRAM costs over the last 20 years have not been going down very fast. CPUs have been going down a lot faster. Moore's Law working much better for CMOS logic than for DRAM. And so that's one of the reasons that today, if you actually the more recently you've done a look at the economics of DRAM versus CPU time, you'll find that reducing memory footprint is far more valuable. And for most people's configurations. And the more micro your microservice, then of course, the more benefit you had from not needing a JVM at runtime, not needing bytecodes at runtime, and so forth.
Yeah, that makes sense. I think there was like a question, or 2 questions ago, there was, or last guy was asking about maybe agent support. Is that?
Yeah, so
there's no agent support.
So I mean, you can link in your like the way people have done things for a long time in native code or for our languages. You just link in a library that does your agent. But the Java instrumentation agent, which was introduced like, I don't know, 5 years ago in Java, or 8 years ago, I can't remember how long it was. 5 years ago was JDK 8. So that agent allows you to dynamically inject bytecode into a running program, and that's not something that we're yet supporting because we are in a bytecode-based system, unless you're running in JIT mode. So of course you can always run Graal as a JIT, the better JIT, but yeah, then you have to kind of do the instrumentation technique you do another language besides Java.
Yeah, okay, and then last question, just from 2 questions ago. I think something about like, if you're running in native mode, there's still some way you could profile. You were saying like on a test system or not in production. Yeah.
So you can.
Do you have any tools or frameworks for thinking about doing that, or is that something that people go build on their own?
You know.
Okay.
Let's go back here. I think I have the invocation somewhere. I guess I had. Yeah, so you basically do native image-pgo instrument, and you run it, and it's going to spew stuff to this file. You basically run it with your test suite, or you can obviously run it in production as was suggested. Okay. But typically you run your tests on it, whatever tests you use to make sure your program's still working. Run it on for a longer period of time so that you aren't just profiling at warm up at startup time, and that's where you can get an advantage with the PGO approach. People do this in the world of C compilers for a long time. Then you take the profile file and you, in the second step, you build that. So this is something you can put into your CI/CD pipelines. PGO optimizations, having this 2-phase compilation step is always kind of a hassle for C programmers now. The way modern CI/CD pipelines are, this is not a big deal to deal with anymore.
No, it seemed to me maybe the biggest deal is just getting enough relevant workloads such that you're not overfitting to some... Right.
Relevant workloads, hard part, but if you aren't testing it, then maybe you shouldn't be running it. But yeah, I mean, obviously, things work. It's not like if you miss part of the profile, things break, right? It's just, you lose like a few % of efficiency.
It seems different than test coverage, though, because you're going to want to have...
Yes.
Like if you have something that happens 99% of the time, or you'd have to somehow weight that in the workload for the profiling to work right.
Well, let me give you a really good example of like where profiling can get screwed up. So you have some common library method, and it has 2 code paths to get to it. The first code path is used mostly at startup, and the second code path is almost used in production. So that's one of the places where Hotspot typically has polluted profiles that make the compiled code worse, because or not as good as it could be, because you're optimizing for the case of the startup, right? That startup path that's using that common library gets weighted very heavily, typically by Hotspot, because during startup is when it's doing the profiling. And once the code is seen as hot, then Hotspot stops profiling because it can't profile native code without a lot of performance overhead. So if you're doing it at development time, when you have more cycles to do the profiling, then you can profile, even when your code has been compiled, with the maximum optimization levels, and then you see really just the hot parts of the program and the executed paths that are most relevant. So that's where we think PGO will actually potentially have benefits over the longer term versus profiling initially at startup.
Thank you.
Sure. More questions? Complaints, comments?
So I would love to know more about what's the term where there are multiple languages you get? Polyglot programming.
Yeah.
Machine learning is very popular these days, and Python is kind of like dominant language for that. What would in future be able to compile those Python libraries within Graal?
In the future, we have samples work. We demonstrated like last year running some SciPy and NumPy logistic regressions or something in the Oracle database. It's a big code we had to make work. I think it'll happen soon. It won't be too long. You have to wait for that, but that's obviously something that's really important. I mean, if you talk to people in the Java group, they're gonna do things, and they're gonna reinvigorate Java for a machine learning language. I think there's so much momentum behind Python as the machine learning language of choice. It's going to be hard by the time Panama is done, and by the time they get libraries there, to really compete with Python as a machine learning language library, as a machine learning language. So that's why we think that Python interop is going to be super important. But who knows? It's hard to predict what people like in languages. One over here.
JVM provides a lot of guarantees around your execution. For example, Java memory model. When you compile the native binary, do you have all of these guarantees?
Yeah, we maintain all the Java guarantees when you ahead of time compile or when you're compiling with the JIT. All the same. That's all done by the compiler in terms of save points and bounds checks and all those sort of things. And that's the compiler that does that is the same in the JIT-compiled case as in the ahead of time compiled case. It's really not. That's not something that's affected by ahead of time versus runtime compilation.
And for other languages, you do the same,
Yeah, so that's, as I said, that's why we added this feature, which is to do the safety properties for native code as an enterprise feature. Of course, we do think over time there's going to be more potential security things you can do because of some of the control points we have. So I showed you some of the embedding, like some of these constraint things. If you're running untrusted code in a sandbox, allowing these kinds of things to be specified per package, per class, setting permissions automatically based on profiling. I think there's going to be a rich vein there around safety properties, especially for languages like JavaScript and Python that often don't come with a lot of guarantees, often just run off and start calling native code via node, and not nearly as much attention has been paid to the security properties of running node as they have been to running native code in the JVM, because it's been around a lot longer.
I've been seeing on the internet lately references to native Scala project at EFPL. Any connection to GraalVM?
No, we are hoping to put the Scala native guys out of business. Actually, we did a demo, I think in July, of using ahead of time compilation with a Scala program to run on iOS. So we showed an iPad running a Scala program. This is a much faster. There's a lot more investment in native compilation of JVM code via Graal than there is. Scala native project was a few people. I think the main committer just took an industry job. So I wouldn't expect a lot more out of Scala native, but who knows? Any more questions? Oh, one over here. Here, I'll just give you that.
Thank you. What about IDE support in your multi-language feature? I mean, if I can directly call some functions from other language. Do you have after completion for that, and what IDE supported?
Yeah, I didn't demonstrate it here, but we do have support for, the question was around IDEs. So we do support the Chrome debugger. I should have showed a demo of that. Yeah, you can, that's one debugging framework we supported. It's really obviously really popular because everyone has Chrome. And we support NetBeans because the NetBeans guys joined the Graal team. So they support Graal. We're hoping, other IDEs as Graal gets more traction, we'll start doing some things. We have a Visual Studio Code plugin that should be released sometime soon. Yeah, that's the kind of the current status. Yeah. No, right now we're behind Java, obviously, when the Java guys come out with new releases, well, we actually the Java team's goal is to get people to use new features of Java. The Graal team's goal is to take people that have a big pile of Java code already and run it better. So that's why we don't actually need to be as cutting edge, but we are investing in it. We will have an announcement along those lines next month. But yes, we are moving faster to get JDK 11.
So you mentioned GraalVM is written in Java. So I'm wondering, did you have to rewrite the garbage collectors or other pieces that were written in C, right, or C++?
Yeah, so the garbage collector that's in native image is written in Java. As I said, it's not as a particularly sophisticated one. We are looking at taking some of the existing native garbage collectors and running them in native image as well. And we'll have some more discussion of that in the next few months. Of the garbage collector? No, I mean, if you really care about garbage collection, you should probably run it in Hotspot. You just use the Graal compiler in Hotspot, and all the languages work in Hotspot as well. So just work in JIT-compiled mode. I mean, the question comes, when is it good to use Hotspot and a traditional JVM? And if you have a big application with a big heap and you want a high-end garbage collector, the stuff that's in the JVM today has been very, very battle-tested and it's very, efficient given the fact that there's some cost you got to sweep under some rug somewhere. In this cloud model where you don't bother garbage collecting, you just turn off the engine and restart it again, then it's not so important. That was the design, kind of the original design goal for native image. But yeah, because people have come along and said, we want ahead of time compilation, but we want it to run on a terabyte heap and we want it to run for weeks and not just, hours or minutes. So that's why we're working on other garbage collectors. But yeah, if you care a lot about garbage collection performance, that's one of the, and you want a big heap, enterprise class garbage collector, JVM garbage collectors are the best garbage collectors, way better than the one in Google V8 or the one in Substrate VM right now in GraalVM. But you can run that way with JIT-compiled mode. Any more? Oh, all right. That's cool. That's a good question. So right now we just do Linux and Mac OS on x86. We are working on ARM. Red Hat contributed an ARM port. So it's in community builds. We're going to make an announcement about that sometime as well. So supporting ARM is obviously important. The other thing we've done is we not only use LLVM as a front end, we can also use it as a back end. So people that have come to us and they want to run on MIPS, they want to run on RISC-V or some other weird architecture, then we generate code via the LLVM backend. It's not quite the same quality. It's not quite, LLVM takes a long time to compile compared to a Java compiler. But it gives you, like if you're doing ahead of time compilation, which is what people care about usually on weird platforms, it's some embedded case. Yeah, I'm running on this processor from, it's whatever, VLIW, there's this French firm that has a VLIW processor that's popular in like Peugeot cars and things like that. So you want to run that, then we'll tell you, use the LLVM backend to generate code. We did that as a research project just to compare the code quality of Graal versus the LLVM code quality. But it's turned out that people wanted weird architectures. So a lot of people that have weird architectures go and put code generation stuff into LLVM now. That seems to be the platform of choice. So that's been real helpful for us.
Yeah.
We have a research project that a student did at Johannes Kepler Institute in Austria, where it's taking x86 binaries, and running it on Graal. It's slow. It's a cool demo, just to show that you can do it. It's not actually that much lower level than compiling LLVM bitcode, which we already support, which is pretty close to assembly. But obviously, x86 binary has all kinds of really weird stuff in it that there's a long legacy of opcodes in x86 that interpreter supports.
Just off of his thing, it reminded me, if there is ARM support or coming, and if there's LLVM compiler, can you then theoretically write a Java application and run it on iOS and Android?
Yeah. I was just mentioning earlier, we demoed last month running a Scala application on iOS. iOS, if you don't know, has this legal restriction from Apple that you can't do dynamic compilation on iOS because security, or because they can't look and figure out what the code's doing. So ahead of time compilation is the only way you're legally allowed to run code on iOS. So we demoed that. It's not something that we necessarily think we're going to support directly, but hopefully someone in the community. There's actually, and I take it back. There's a small company called Gluon that actually is supporting now, or I don't know to what degree it is supporting GraalVM on iOS. I don't know what the status of Android is, but they demoed iOS first. More questions? This is great. All right, well that's I guess plenty. I'll stay around afterwards if you have more questions one-on-one. Thanks.